In this short lecture, we are going to look at transfer learning and adversarial learning in convolutional neural networks. We have seen that training convolutional neural networks from scratch requires extreme resources, such as millions of images, clusters of GPU, and lots of time and money. Now, there are many situations where one cannot have that many resources available for a given application. So in such situations, it's the transfer learning that becomes handy and useful. So let's see what is transfer learning. As the name implies, transfer learning actually transfers knowledge gained by a convolutional neural network via training on one problem to another problem or another domain. So basically, you start with an existing trained network, and whatever knowledge that trained network has captured, you try to transfer that knowledge to another application or another problem. Basically, there are two transfer learning approaches that are followed. One is what we call as fixed feature extractor approach, and another approach is known as the fine-tune, the CNN approach. So let's look at these approaches. Transfer learning fixed feature extractor approach. So in this approach, let's take an example that you need to create a classifier system for doing flower classification, but you don't have enough data, as well as you don't have enough resources to go and collect more data and annotate that data. So what you want to do in such a situation is that take a trained network, for example, take the LXNet or VGGNet, and in that trained network, remove the last 2 or 3 layers where basically you have fully connected networks that are taking care of classification. So take the output that is coming from the last convolution layer and treat that output as a set of features for a given input that is presented to the network. So what you can do is you can take your small set of examples, feed those examples to your trained network, and get the output written into a file at the last convolution layer. And once you have that file of outputs, basically that's a file of feature vectors for inputs to the system. And what you can do is you can take those feature vectors and use some other simple linear classifier, for example, logistic regression, to perform your classification task. So this approach is known as the fixed feature extractor approach, where you are making use of a trained convolutional neural network as a feature extractor. And those features are then used to design a classifier in the traditional machine learning approach. So this approach works pretty good for situations where the number of examples is really small. The fine-tuning approach is the other approach. In this approach, what you do is you take a trained network and generally you remove the last layer where, for example, if you are working with, let's say, LXNet, the last layer will have 1,000 neurons because that network was trained for 1,000 classes. Suppose you have a problem where the number of classes is only 100. So what you will do is you will replace those 1,000 neurons with a layer of 100 neurons, and assuming that you have decent number of examples that you can use to train for your given application, what you do is you basically present those examples to this network that you have modified at the final layer and run through few iterations of adjusting the weights or the parameters of this network. So in a sense, you take an existing trained network, modify the output layer for your given application, and then perform little bit of fine tuning on this entire network so that this network is able to perform well for your given problem. Again, the basic idea behind transfer learning, whether you're following the feature extractor approach or fine-tuning approach, is that these networks that are trained like LXNet or VGG or ResNet or any other net, these networks basically at the lower levels of, at lower convolution layers, they try to capture features from images that are fairly generic features. And as you move towards the end of the network, the features or the information or the knowledge captured by such networks is more and more domain specific. So what you can do is you can remove the last layer or last two layers and basically retrain the network with new last one or two layers and make some adjustments to the network so that it can perform well for your given problem. So that's basic idea of transfer learning. What we are going to do now is we are going to go over an example of transfer learning. In this example, we will take a trained network, which is a Res 18 network. Remember, this Res network, there are several versions depending upon how many layers you have. So Res 18 is one of the versions which is on the lower end of number of layers in the network. So this network has been trained on CIFAR 100 data set, which has 1000 classes. So what we will do is we will take that network and we will keep the feature extraction layers intact and train only the output layer. And in this case, we will train the output layer to perform a two-class image classification. And the image data for these two classes consists of images of ants and bees. And this example is taken from this PyTorch tutorial, so you can actually go and refer to that tutorial later on if you want. So in order to perform transfer learning for this particular example, the first step is always the same. That is, you need to load all the necessary libraries that are needed for your work. Step 2 will be basically downloading the data. So in this case, the tutorial also provides a link from where you can download the data. So basically, we download it and save it in a directory. And if we browse through the data, you will find that there are about 120 images of ants and 120 images of bees. And these images are for fine-tuning or for training, you can say. And then there is another set of images, 75 per class. And these are for validation or test images. Now, these images may not be in the size that the network expects at its input. So first thing what we need to do is to get these images into proper size, and at the same time we also need to normalize them. Sometimes what you may want to do is you may want to perform some data augmentation steps so that you have an effective increase in the size of your data. If you remember our discussion on LXNet, that is what people did in LXNet. They basically took the data and applied number of different augmentation steps, including rotation, translation, etc., etc. So similar steps can be applied here so that we can actually effectively increase the size of the data. And since it's a Res 18 net, so the size that we need is 224 by 224. So basically that's what will be done in step 3. And of course the images need to be converted to tensor and they need to be normalized and all that. And we have seen how to do those operations earlier. So in any case, that's basically the set of steps or the set of code lines that you need to use to perform data transformation. Next step is basically to load the data into data loader and specify what batch size we want to use. And of course, as we've seen earlier, data loader supplies images for training to the network in batches of specified size. And also, of course, it does the shuffling so that things are not presented in the same order all the time. The number of workers parameter specifies how many batches can be fed in parallel to the CPU. In this particular case, I think the batch size is, let's see, where is the batch size? Batch size is 4. And also the number of workers is 4. So basically 4 images will be presented in one batch, and of course there will be 4 batches that will be presented in parallel. This is just a step to display some of the training images and their labels, and the lines of codes is pretty standard. We have used that code or similar code before to convert tensor to NumPy and all that, and display the images. Step 6, basically what we'll do is we will define a function for general training procedure, learning rate scheduling, and also saving the best model and printing training time. We just want to get an idea of how much time does it take to train. And of course, this function is fairly general or generic. And what you can do is you can use this function for any other training application that you might be working on or you might work on later on. And this function is shown on several slides because it doesn't fit on one slide. So next few slides will basically show this function. And steps in these functions are pretty standard. Again, we have seen them, some of them in our earlier assignments where we have trained some models or networks with number of images, presenting them in batches, looking at the accuracy, feeding back adjustments for weights and all that. So that's step 6 continued on several slides. And on this slide towards the end, you can see we are calculating how much time it is taking and what is the best accuracy, etc. And these pieces of information will be printed as we go along. Step 7 basically is now getting the pre-trained model. So we download this model from ModelJew that is maintained by PyTorch and set this model up for training. So you will see here we are getting this model over here, downloading it for our use, and we are specifying it's a ResNet 18 model, and pre-trained is equal to true means this model will not be trained. Its weights and parameters are fixed. And again, the setting the parameter requires gradient setting equal to false again indicates that no changes in the parameters will be made. All right. And over here, we are defining a new classification layer for our problem because we only need we only have 2 classes. So basically our output should consist of only 2 neurons. So that's basically what we have defined here. And we are going to be using cross-entropy criterion for doing the training. And over here, we are specifying which optimizer we are going to be using and any scheduling in terms of decaying of the learning rate, etc., as the training proceeds. So all those pieces of information are specified over here. So next step is simply train the model. So in this case, as the model gets trained, we are looking at the output. We are printing out the loss on training as well as on the test or the validation set. And we find that after going through 25 epochs, the training loss is about 0.3506, which translates to the accuracy of 84.84% on training data. And test loss is 0.2049, which basically translates to accuracy of 94.12%. And the training was completed in 16 minutes and 22 seconds on my machine, which is in Mac desktop. And the best accuracy that we got was 94.77, which possibly was at the end of 23rd epoch over here. So that's basically what we have. That's basically how you will do the transfer learning. Let's just check performance on test data. So basically what we are doing here is just feeding the test examples and seeing how well the network is responding to those examples. And here we show you some results of transfer learning. Basically, there are 4 images because batch size is 4, you remember. So basically that's what we got. For one batch, we got 4 images that are input test images, and we are showing you what the predicted labels are. And you can see that our system after transfer learning is doing a pretty good job. So let's summarize transfer learning. So transfer learning is widely used in many deep learning applications. And the reason for that is obvious, that is the data size and time limitations are present in many situations. So to overcome those limitations, transfer learning is a nice way of dealing with those situations. One can also use transfer learning to perform a quick check on the difficulty of a new image classification problem to decide whether you want to go for a full-blown effort or not. Because if transfer learning doesn't give you very good results, then you might need to collect more data and maybe, train the network from scratch. So it depends on the problem. So it kind of gives you a quick check. So that's basically what I had to say about transfer learning. Now let's switch gear and talk about another kind of learning, which is known as adversarial learning. Now this topic by itself is a very important topic because what this learning represents a situation where you have a bunch of good guys and you have a bunch of bad guys. Let's think of, people trying to spam emails and send to users, hoping that users will click on their spam emails, and as a result of that, either their systems will get infected or they will basically be able to provide some monetary gains to people who are sending those spam emails. For spam filter, the idea is that we need to block all such emails that are suspicious, that might look like that they are real emails coming from good, genuine people, but in reality they are basically spams or emails that can create problems for the user. So basically both sides are trying to defeat each other. So in such situations, if you are designing a system, you want to know how your system can be defeated. So in this short few slides, we are going to look at a situation where it is possible to create pictures or images that will lead a trained convolutional neural network to output incorrect results. And design of such examples is actually part of adversarial learning. And later on, when we talk about generative adversarial networks, again, we'll come back to the idea of adversarial learning. So basically, what we are trying to do here is to intentionally create examples that will cause a system to fail. And basically, in a way, we are trying to poison the input so that the system will fail. And such failures can have very serious consequences. Think of an autonomous system or autonomous vehicle which basically reads the road signs through visual sensing, and then there is a visual recognition system in the vehicle which basically figures out what's the meaning of those signs. So if one can poison the input, for example, if one can do something to the stop sign, make some changes, minor changes to the stop sign, such that a trained convolutional neural network will not recognize it as a stop sign, but rather recognize it as a sign which says that you must maintain a minimum speed limit of 40 miles, then obviously you can think of all the harm that will be caused by such an manipulation of the stop sign. So adversarial learning, adversarial attacks, these are very important issues and very important problems of interest to lots of researchers. So we can think of two scenarios for adversarial learning, and these are two broad scenarios. One scenario is known as the Whitebox Scenario. In this scenario, we assume that somebody who is trying to create issues for the system or who is trying to attack the system has full knowledge and access to the model, including the architecture, inputs, outputs, and weights. And second one is what we call as the black box scenario. A black box scenario assumes the attacker only has access to the inputs and outputs of the model and really has no idea of the underlying architecture or the weights of the model. We will look at a particular technique here, which is known as the fast gradient Sine attack technique. And this technique assumes that we are working under the white box scenario. That means this kind of attack is going to be performed by some insider and not by some outside person. And the idea here is to use the gradient. Typically what we are doing when you are doing the gradient, we have a loss function and we basically use the gradient to move in a direction which will minimize the loss function. But when we are talking of fast gradient Sine attack, we flip our aim. So we use the gradient not for minimizing the loss, but we use it to maximize the loss. Now, in order to maximize the loss, what do we need to change or modify? We take the inputs that the network is expected to work with, and what we do is we modify these inputs, we distort these inputs a little bit through gradient search to maximize the loss. So that when the network looks at these perturbed or disturbed or modified inputs, it will produce an incorrect result. Here is an example of what we are talking. So let us say that we take an image of a panda. The network has been trained on this image, and when we present this image without any perturbation, the network has a 57.7% confidence in this image that it's a panda image. Suppose we disturb this image, or we add to this image a noise pattern which is derived through gradient search for loss maximization, and that noise pattern looks like this. And if we add that to the panda image with a weight of 0.007, we get a new image that looks like this. Now, if you look at this image through a naked eye, there is no differentiation that you can make. So this image looks just like our original panda image. But when this perturbed image is presented to the network, we find that network does not recognize this image anymore as a panda, but it recognizes it as another animal called gibbon, and it does so with 99% confidence. Of course, in this case, you can say, well, it's just one animal, another animal, so not a big deal. But think of a situation where this image with noise could be made such that the network will recognize this as some other object, which with that recognition, the network might create some issues down the road where the network is being used in a given application. So this can be really very tricky, and doing this manipulation of the input image is pretty simple and not very difficult. As we saw, basically what we are doing is we are taking the starting image and we feed it to the network, and as we get the gradient values back all the way to the input layer, what we can do is we can take a very small fraction of those gradient values and add them to our input image to create a new or a modified or perturbed image. So the line of code for this particular one is pretty simple, shown here. Just 3 or 4 lines can basically accomplish this. So suppose we do this and we take the LeNet, which was designed for doing digit recognition, and we make some changes to the images that were used for training the LeNet. And of course, to see what is the effect of this epsilon value, because you are adding the gradient weighted by the epsilon value. So if the epsilon value is close to 0, obviously the effect will be very, very little. If the epsilon value is relatively higher, you can create more perturbation to the image. It's still not visible to a human eye, but good enough for the network to basically make a wrong decision. So basically the idea of a previous slide of perturbing has been applied on the LeNet, and basically this slide shows you the result. So if you look at with epsilon 0, basically means you are not really doing any perturbation. So 3 is recognized as 3, 1 is recognized as 1, and so on. Let's come here to the last row, where the epsilon value is 0.3. Now in this case, you find that the 4, the digit on the input side is 4, but it is now being recognized as 8. or 8 is being recognized as 4, or 2 is being recognized as 8, and so on. Of course, here the noise is little more, and you can actually see it in the image. But check out here. This is epsilon value of 0.15. Here the perturbed image doesn't look different from the original image. So this 7 is being recognized as 2, this 9 is being recognized as 8, and so on and so forth. So the idea is that through perturbation of the input images or expected input images, what one can do is one can make the convolutional neural network respond incorrectly. If you want, you can go and take a look at this site where you can see the full code and this tutorial on this. There is another way of creating adverse examples, and this is a relatively recent approach. What people have seen is that they have seen that they can design small patches that can be attached or affixed to a scene that is being captured by the camera, which is part of your convolutional neural networks system. And these tiny patches or small patches can be designed in such a way that they can force the convolutional neural network to produce an incorrect response. So here is an example of what you will call as a real-world attack. So here is an image of a banana sitting on a tabletop. And when this image is presented to a trained convolutional neural network, the network comes back with a very, very high degree of confidence, almost 100%, saying that it's a banana. Now, this specially designed sticker, now if it is placed on the table close to banana, and the picture is taken again, in this case, the network comes back with a decision that this is the image of a toaster. And it has a very high confidence in that, while this is the image of a banana, that confidence value has gone to almost 0. And why it is coming back as a toaster? The reason for that is that when this patch was designed, you can actually specify how you want to adjust the values in this patch so that whatever disturbance those values cause to the neural network, those disturbances will lead to a desired output incorrect classification. So in this case, the patch was designed so that the convolutional neural network will come back with an answer as a toaster, which of course is a wrong answer when it is looking at that scenario where actual object is banana, but it comes back with an answer of a toaster if the patch is also present next to banana. Here is another interesting example, and you can say that, do you want to be invisible? Now, you know that there are cameras everywhere, and these camera feeds are processed in real time or later on for locating all the persons that are present in those images. So suppose you want to become invisible. That is, you are there, but whatever person detector is being used by a system, that system is going to miss you, and the system will come back with a response as if you are not there. So in this picture, if you look at this picture, in this picture we have two persons, and this picture is being fed to a person detector system, which is built using a convolutional neural network. So in this case, one person is wearing a special patch, and one person is appearing just like in a normal life you will appear. So what the system is doing is, the system is not able to recognize the person who is wearing a patch. So the answer for this picture from the system is that this picture contains only one person. That means the person with the patch has become invisible. So again, this is something that could be put to a malicious use in certain situations. So basically what is going on in terms of adversarial learning is that there are people who are trying to think of what are the different ways in which we can degrade the performance of trained networks or performance of these AI systems. And there are a group of people who are, of course, coming up with techniques that will overcome these kinds of attacks. So all those methods and techniques are part of the field of adversarial learning, and obviously that by itself is a pretty big field. But this over here is just a tiny introduction to that field to give you an idea that it is not very difficult to have convolutional neural networks go wrong. So we will stop here. Thank you.